Yes, sir.
My slide is also visible.
Yes, sir.
Okay. So we started discussing the measurement of high resistance, and briefly we discussed the issues. Although we were discussing the different issues which we are supposed to deal with if we are measuring the high value of resistance. Generally, as I told you, that high value of the resistance is either discrete resistance or resistance of insulation. Generally, it is resistance of insulation. So leakage current is one of the major issue that I had asked. Even if we are talking about the insulation resistance, so we want that the conduction current that is going through the body of the insulation resistance we are interested in, and whatever current which is flowing um, through the surface of the insulation, that we are not means that will lead to the error. So leakage current is main challenge, one of the main challenges in measurement of high resistance, and we basically require some method, some means, so that we can avoid, I would say avoid, because the method which is used to um, tackle the leakage resistance, it basically avoids the leakage current. So leakage current is one of the pertinent issue. Then stray, because as I told you, that when we are making a connection with the insulation for measurement of resistance, then a capacitance formation will take place, because we'll have one conductor connected at the one side and another conductor at the another side. In between, you are having very high resistance. It may be insulation resistance. So uh, 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 um, capacitance formation will take place, and if there are stray charges on the conductor, you can say, on the electrodes, so that will lead to the error. This is another issue. And generally in in high resistance measurement, we short the electrodes to the ground before starting the measurement, so that if there is any stray charges, they should get grounded. uh, we short both the terminals also, so they recombine if there is any charges are there. Then there is issue of um, uh, charging current. Means if you are connecting a capacitance, uncharged capacitance to the source, DC source, then at the starting, huge amount of charging current flows. So again, this charging current we are not supposed to, because this is not conducting current. It is a transient phenomena that takes place for some time. So it is very important that while taking the reading, we should wait for some time. Means once you energize the circuit, then you wait for some time. So after some time, your charging current will diminish. Then I talked about the dielectric absorption. Actually, what happens, there are the charges inside the body of the insulation also, and these free charges are there, and it takes some time that these charges, they get recombined with the positive and negative charges. So it takes a lot of time, sometime even hours. It takes hours. So but dielectric, there is no other way to get rid of dielectric absorption current. We have to wait for some time, so that majority of the free charges that is trapped inside the insulation body, they should get absorbed. So this way means charging current and dielectric absorption current, these two currents are means once you will apply the potential across the high resistance or insulation, then charging current and dielectric absorption current, it will subside after some time. So after you see main issue means we should be careful, means main issue is your leakage current. Leakage current is basically the most potential cause of error, because if we are talking about the stray charges is not much, but at the starting, if we are shorting the terminals or grounding the terminals, then these stray charges will get away. Then as far as charging current is concerned and dielectric absorption current, you should wait, we are required to wait for some time after energizing the circuit, so that your charging current and your dielectric absorption current should subside. Then finally your leakage current remains over there, and we require a special method for to take care of this leakage current. We don't want that leakage. So a guard circuit is used to divert the leakage current, not to stop the leakage current, but to divert the leakage current. So we'll discuss it this. This is guard circuit arrangement, you can say. It's not a dedicated kind of circuit. Only what we do, we try to provide the separate path for the leakage current, so that our meter should not get, means we want to provide the here in the guard circuit arrangement, we provide separate path for the flow of leakage current, so that your meter should not read it. So here this is the conceptual diagram, circuit diagram has shown. Here you see, if we are not using any guard circuit, then what will happen? This is your leakage current, which I tried to show you in form of circuit diagram. It flows through the surface of the insulation, and this is the current which we are interested in finding out. It is flowing, it is actual conduction current, and it is flowing through the body of the high resistance, you can say, or insulation. So this indicates basically this conduction current, which is flowing through the body of the insulation. It indicates. And another thing I forgot to mention, that as far as leakage current is concerned, leakage current is not constant, because it is flowing through the surface of the insulation. So it is means existence of leakage current itself is a problem as far as the measurement of high resistance is concerned. And in addition to its existence, it is variable also, because as the environmental condition will change, the surface condition will also change, and accordingly your leakage current will vary. So leakage current is not constant. It is basically means like if there is a rainy season or if there is a snow, then obviously your leakage current will be more, and if there is a dry condition, then it will be less, and if there is a pollution and everything. So this is a leakage current is a big pain in the neck, you can say, as far as the measurement of high resistance is concerned. So here this is the situation when the guard circuit arrangement is not made. So guard circuits are used for to tackle, you can say, that the leakage current. And here you see, we are taking microampere, because in the insulation testing or high resistance measurement, resultant current will be very small, and the applied voltage you always require very high. so you can see that ammeter is reading both your leakage current as well as your conduction current, and this conduction current and leakage current is of the same order, you can say, and that's why we are very much concerned. Now what is done here, the conceptual solution has been shown. Here we are guarding a circuit, terminal of the circuit. your insulation. So you can see that the path, you can say the path through which your leakage current flows, it is basically guarded with the conductor, and this guard conductor is basically at one side it is grounded, at other side it is connected to the means it is before the ammeter it is connected. So situation is that your conduction current will flow through the main terminal and through the ammeter, and your leakage current will get bypassed through the guard circuit to the ground. So this is what is done. Obviously it is not a dedicated kind of circuit, but it is a guard circuit arrangement. For different kind of insulation systems, different kind of arrangement is made. That I'll show you. Don't worry. So at this point of time, this is what I want that you should understand, that if it is we are not using the guard circuit to take care of the leakage current, then obviously your ammeter will read both the currents, leakage current as well as conduction current. When this kind of arrangement is required, where the guard circuit is used, which surrounds the basically the terminal of the resistance, and guard circuit is grounded, and another side this circuit is so we are basically providing the alternate path for flow of leakage current. Instead it should go through pass through that, and it will go to the ground, and it should not pass through the your ammeter, current measurement device. So this is what is the concept of guard circuit. How it is implemented, we'll see. Okay, so if anybody is having any question regarding the guard circuit, you can ask, please. So as usual, you are not having any query. Now, as far as methods are concerned, three different methods are used: direct deflection method, loss of charge method, and mega ohm bridge method for measurement of high resistance. Loss of charge method is considered as the best method for measurement of the measurement of high resistance. And I'm starting with the direct deflection method. Direct deflection method, you can say that it is a basically voltmeter ammeter method for measurement of high resistance or insulation resistance. So in this case, you see, obviously very high voltage DC voltage is required, and we are measuring cable insulation resistance. So this is your core, your conductor of the cable. This is your insulation, and sheath material is means sometime you'll find that your outer cover of a cable is basically the conducting sheath that provides the protection to the cable. So if we want to know the this insulation of the insulation resistance of the cable, then obviously we require two electrodes connected to the insulation. So here both the electrodes are already there in the cable itself. One electrode is your conductor of the cable. It is in contact with the insulation, and at the other side it is sheath. It is also made up of conducting sheath. So so you can say that two electrodes are here, one at one side, and in between your insulation is sandwiched. This insulation at one side is your conductor, cable conductor. At other side it is your sheath. So you can see that we are connecting. This is the circuit. We are connecting the sheath. No, sorry. In supply, then supply is connected to the inner conductor, and then return path is through the sheath, and then this circuit is complete. So basic circuit is like this. This is voltmeter ammeter method. You can see we are connecting our voltmeter across the supply, and then a galvanometer. Why we are using galvanometer instead of ammeter? Because the current is very small. So either we use micro ammeter, because this is an insulation, and very small current will flow. If your insulation is good, then you don't expect that in microampere. If and that too happen if you are applying very high voltage here, only then this. So it is either microampere, so galvanometer, or microampere meter, and then this is then this circuit is completed. You can see that we connected, instead of ammeter, we are connecting galvanometer here, because of very high sensitivity is required. And then here we are going to the insulation. After insulation, this is a return path through the sheath, and this circuit is completed. Now we are looking some additional extension out here. One is this and another is this. So this circuit is basically guard circuit. You try to understand whatever conceptual diagram that I had shown here, how it is physically implemented. You can see that because your current will flow, always your leakage current will flow through the surface of the insulation. So this surface of the insulation is connected here, and leakage current will flow through this path. It won't go through the galvanometer or the microampere meter. So leakage current, so this is called guard circuit for this particular guard circuit arrangement for this particular application or testing. So if anybody is having any query, you can ask. This I tried to show you the guard arrangement here, which takes care of. So you can see that the leakage current will flow through this, and it will return through the sheath, and your conduction current will also flow through the insulation, not through the surface, and it will. And you can say that your leakage current may flow from conductor to this path. It can take this path. I'm telling you, this path means your leakage current can take this path. So that is not possible, because when you are providing the guard circuit, then you see potential of this surface and potential of this surface will remain same. So your current won't flow. The current always flows from the higher potential to the lower potential, because this is also at the same voltage and this is also at the same voltage. Both of them are, you can say, it's sort of parallel. So no current will flow through this. Whatever current, leakage current that will flow, that will take this path only, and it will go to the sheath, and then it will come. So here you can see that here we are having leakage current as well as conduction current. Your conduction current and leakage current. And here also we are having both. In between, it is bypassed. Leakage current is bypassed through the guard circuit. So if anybody is having any query, anything you are not able to understand how this guard circuit arrangement is implemented here, you can ask, please. जी बताइए, कोई क्वेरी है आपकी? अच्छा, मेरी एक क्वेरी है, ये बताइए कि ये स्विच क्यों लगाए हैं? ये स्विच क्यों लगा दिया है यहाँ? हेलो भाई, जग रहे हैं आप लोग?
यस,
बेदार हैं, चलिए अच्छी बात है। ये स्विच क्यों लगा हुआ है यहाँ पे? अच्छा, स्विच क्लोज हो जाएगा तो क्या होगा?
गैल्वेनोमीटर वर्क नहीं करेगा
जी
सर, गैल्वेनोमीटर शॉर्ट हो जाएगा सर।
तो फिर क्या होगा? शॉर्ट होने से क्या होगा?
सर वो रीडिंग नहीं देगा।
क्या नहीं, रीडिंग नहीं देगा? अच्छा,
यस।
इसको क्यों लगा दिया है? मतलब आप ये कहना चाह रहे हैं करंट गैल्वेनोमीटर के बजाय इधर से फ्लो हो जाएगी, है? क्योंकि शॉर्ट शॉर्ट सर्किट कनेक्शन है ना, आपका कंडक्शन करंट इधर से हो जाएगा। कोई बता सकता है भाई ये स्विच क्यों लगाया है? भाई चार्जिंग करंट की भी तो प्रॉब्लम होती है जब इनिशियली आप डीसी वोल्टेज सोर्स लगाएंगे तो बिकॉज क्योंकि यहाँ इसको भी ग्राउंड कर देंगे तो ये चार्ज कोई होगा तो ग्राउंड हो जाएगा, तो इसको फ्रेश कर लेंगे, है? हम पर्च कर लेंगे और फिर उसके बाद ये, तो जब जैसे ही हम लगाएंगे इसको तो लॉट ऑफ चार्जेस, बिकॉज बोथ both the electrodes are basically not having any charge, so lot of, because this sort of capacitor formation is taking place, so initially a lot of large amount of charging current will flow. This is the phenomena you will always see when you are using capacitance, connecting any capacitance to the any DC voltage source. So initially large amount of current flows, and if that current will flow through the galvanometer, then it will damage the galvanometer. So initially what we do, we short it, and then we let the charging current, large charging current to flow through the short circuited means circuit, through the this conductor short circuit path, and it should avoid the galvanometer or microammeter. And so and then we are having your charging current as well as your dielectric absorption current, and we'll wait for some time so that your charging current should subside and your dielectric, then we open the switch, and then we take the reading. So this is how basically experiment is done with this is a direct deflection method, and this is how we avoid the leakage current, and this is how we take care of charging current and dielectric absorption current. Now another experimental setup I had shown here. In this case your cable is not having conducting sheath, then cable, this is all basically called insulation testing. Then this cable is basically put into the liquid, and there is a standard method which defines how much time you should dip the, so this is a conducting liquid, and your return path obviously will be through the liquid. So in this case you see, you can see that this is the guard circuit. Here you see this is a conductor at one side, this is a conductor at other side, your metallic tank and liquid. So this is making another electrode. So in this case you see again this guard circuit is here, this is the guard arrangement, and regular circuit is this circuit, and your current will flow through the insulation to the liquid to the tank, and it will be returned to the supply. This is how this circuit will work, and this is the leak, because you will see that your leakage current may flow through what conduction current will flow through the body of the insulation, and leakage current through the surface of the insulation. So to avoid that, this guard circuit arrangement is used. This is all guard circuit arrangement, and it will make sure that the no current should flow through the galvanometer. It should pass through the guard circuit, and your galvanometer reading or the microampere meter reading should be free from the leakage current, and that is what is our objective. So this is how guard circuit is used in insulation resistance measurement, and this is how other factors which are not that much prominent, but still they are present with that is your charging current, and which through this short circuit we try to avoid the charging current, and these charging current and dielectric absorption current, these are the you can say that transient phenomena. They are not permanently present all the time. they initially they flow, and after some time they subside, but leakage current continue flow throughout the time uh, when your circuit is energized. So for that we are using guard circuit. So this is how guard circuit is used, and other factors are taken care of in direct. And this is this method, whatever I try to show you here, it is basically the voltmeter meter method modified for the measurement of high resistance. So if anybody is having any question regarding whatever I discuss about the guard circuit arrangement and direct deflection method. जी, कोई क्वेश्चन है आपके पास? नहीं है? आगे बढ़ा जाए? जी, इजाजत है आगे बढ़ने की? अच्छा, चलते हैं, आगे बढ़ते हैं। तो जो बला बला हमने किया है ये सब यहाँ लिखा हुआ है। और now the second method is loss of charge method. So in this case, this method is very, although this is a special method, it is not modified version of any medium resistance measurement method, but it is an original method for measurement of high resistance or insulation resistance. So here in this case, this is your unknown resistance, and then we connect a capacitance across it. Then we take the voltage source, obviously large voltage source is required, and then we switch it on. We connect the switch. Switch is on, then what will happen that this capacitance will be charged to up to certain potential, depending upon the value of the voltage of the voltage source. And then this, after some time, this switch is it is open now after some time. Now main experiment will happen. This, after when your switch is open, then this charge capacitance will get discharged through this insulation, and that discharge readings will take with respect to time through this voltmeter. Generally this voltmeter is electrostatic voltmeter because very high voltage is there. So by measuring the time, and so this is a RC circuit you can see, and by measuring the time and voltage we will draw exponentially diminishing voltage. So through this curve we will be able to find out, because we know the time, we know the voltage, so we can find the resistance. So how what is the expression and how we do that basically, so experiment is this. And you see, anyway, so this is how experiment is conducted. And so we note down the voltage, your discharging voltage, your diminishing voltage across the capacitance, and the time. These two things we note down. Now I try to explain here. Let V be the capacitor terminal voltage, that is basically reducing with the respect time, varying with the time. Voltage at any time, Q be the charge in coulombs. Q is the charge still remain on the capacitance. So current I at any time t will be equal to minus dq by dt. Why minus? Because here your charge because this is the equation which is defining the discharging current, not the charging current, discharging current. So obviously whatever charge which is present on the capacitance, it is getting discharged, diminishing through the resistance, unknown resistance or insulation resistance. So this is your current, and so you know Q is equal to CV. So C is constant and V is varying with time, so dV upon C minus C dV, and minus sign is for diminishing. And you know, I is equal to this current is, if we take the current in this circuit, then this is the relation. This is the relation. Now if we are talking same amount of current is flowing through the resistance, then this resistance obviously here it will be, current will be V upon I, where V is the voltage across the capacitance, and same voltage will appear across the resistance also, because both of them are in parallel. So you see that here same current will be V upon R. So we equated both of them, then we got this differential equation. When we solve this differential equation, then we'll get this. So in this case, in equation, if you look, this is the solution of this differential equation. If you look, we are having initial, up to the initial voltage up to which your capacitance is charged. This is the voltage with respect to time, and with respect to time we are taking the reading. Capacitance value is known, so only thing which is not known is R. So through this equation we can find out, if we know the voltage across the capacitance and time, and the capacitance value itself, then we can through this expression we can measure the value of unknown resistance. So this is what is the basis of this method, which is called loss of charge method. So I modified this, simplified rather, this equation, and then finally we found R is equal to T. So this equation very easily can be used for measurement, and if we don't want that log base E, then in terms of log base 10, this. So both the equations are same, only difference is here it is log base E, and this here is log base 10. Now how this is done, I'll try to explain it using this example, numerical example. So here you see capacitance value is 0.2 microfarad, and the voltage source which is you are using, it is 400 volt, and then you see time taken for the capacitance terminal voltage to fall to 250 volt in 1.5 minutes. Means your capacitance is charged up to the 400 volt, and then your switch is open, then this will get discharged, and it takes 1.5 minutes to get discharged to 250 volt. That's what it has been told here. So initially it is 400 volt, and then it is discharged. So if you look at this expression, so capital E is 400 volt and small v is 250 volt, and t here time is 1.5 minute. So determine the value. So you can see that through this equation, all these parameters we are getting, and then we are putting here, so we can calculate. So that is what is done here. So if anybody is having any question, you can ask, please. हाँ भाई बच्चों, कोई क्वेश्चन है आपका? सोचो अच्छा, तब से मैं कुछ लोगों की अटेंडेंस ले लेता हूँ. You think about it, try to absorb, try to find out any confusion you are having. Now respond your roll call, please. Roll number 1.
Present, sir.
2.
Present, sir.
3. 4.
Present, sir.
5.
Present, sir.
6.
Present, sir.
7. 8.
Present, sir.
कौन है भाई? कौन है लेट कमर? Knocking the door. जी कौन है? Who is asking permission? Somebody is asking permission. Or some message I got. Mohammad Arshad Faizi. Roll number 3. Okay. Faizi साहब.
एक्सक्यूज सर.
हाँ बताइए.
सर इसमें सर हमने कैपेसिटर को रेजिस्टेंस के और वोल्टमीटर के साथ पैरेलल में कनेक्ट किए हैं.
जी
सर तो जब हम स्विच को ऑन करेंगे, सॉरी ऑफ कर देंगे, मतलब ओपन कर देंगे, तो उसके बाद जब कैपेसिटर डिस्चार्ज होना शुरू होएगा तो लास्ट वाली स्लाइड में, तो उसमें सर जो करंट जाएगा सर वो हमारे जो रेजिस्टेंस मेजर करना चाह रहे हैं आर से, उसमें से भी जाएगा सर। सर कुछ अमाउंट वोल्ट मीटर में से भी जाएगा। तो सर क्योंकि दोनों ही बहुत ज्यादा हाई
देखो इलेक्ट्रोस्टैटिक यूज करते हैं, वी आर डिस्कसिंग हियर with the assumption that no current is flowing through the voltmeter, ideal condition we are assuming. So whatever current that is flowing, that is getting discharged from the capacitance, it is entirely flowing through the resistance. So that's what is the assumption and through which we are getting this expression. अब आप क्या पूछना चाहते हैं?
नहीं सर वही तो मतलब अगर उसको करंट मानते सर फिर टाइम पे इफेक्ट पड़ता है उसके, तो फिर रेजिस्टेंस की वैल्यू अलग आ जाती है।
That you are correct that if you are going to measure your, but your current is so small, and this
No
amount.
sir, actually both the resistance are in the same league, means resistance of the R is quite large and the voltage meter resistance is also quite large, so the amount of the current need to be quite similar in amount. No?
This is a issue. This is an issue that many times you will find that there is no discharge. You won't find any diminishing in the reading, because this is an insulation. You assume this is an insulation. So very small current is flowing or no current is flowing. So very long time you will find many times in up to hours you won't find any significant change in this voltage. If there is a problem with the insulation, obviously then the current will flow and then you will find it that it is. So this is a issue, and that's why some other arrangement is done that I'll discuss. But as far as the original means method is concerned, this is the method. Anyway, this is how we find out and this is how this experiment is conducted. Now right now what we are doing, we are noting down the voltage which is diminishing, discharging through the resistance, unknown resistance, and time. So you will see that after conducting the experiment you will have this kind of curve, and from this curve you can find out any value you can take, and then but generally instead of this we take this equation. So if you look at this equation, this is a straight line equation. So if we are drawing a curve between log v and t, means this is a y is equal to mx plus c, mx plus c, है ना? So instead of drawing the curve between voltage and time, we draw the curve between log of the voltage and time. So advantage of this curve is that for drawing this curve you require many data points because it is a non-linear curve. Here it is a straight line, so you require only two readings. You require, हाँ भाई म्यूट कर लें आप अपने आप को, there is a lot of disturbance. So generally if you will find that instead of drawing the curve between V and T, testing, because this process, the method is called testing, because generally this method is used for insulation resistance testing, insulation testing. So by measuring the insulation resistance, we try to find out the quality of the insulation. So that's why I'm calling it testing. So generally this testing results are shown in graphical form instead of the tabular form, and this instead of having a graph between V and T, why I'm requesting to all of you that you should mute yourself so that we should not have. भाई जीशान खान, जीशान साहब, रोल नंबर 8।
सर ज़हीम खान, सर ज़हीम खान।
ज़हीम, सॉरी, हाँ ज़हीम खान, आप म्यूट कर लें अपने आप को। ज़हीम साहब दुकान में बैठे हैं भाई साहब, लगता है बिजी हैं।
सर आपके पास भी ऑप्शन होगा म्यूट का।
अच्छा हमारे पास होगा ना ऑप्शन। सही कह रहा हूँ। ज़हीम खान साहब को म्यूट कर दिया जाए। म्यूट का तो है नहीं, रिमूव का है।
सर ये जो ब्लू सर्कल है उस पर क्लिक कीजिए।
अच्छा अच्छा, ठीक है, ओके ओके। तो आज ज़हीम साहब को एब्सेंट कर दिया जाए। ठीक है, चलिए। तो क्या बात चल रही थी, मैं तो भूल ही गया। हाँ, इसमें इसमें we generally, so you see what is the advantage of this curve, because this is the form in which you will get your observations. So here, to find out this curve, we require only 2 data points on, because this is a straight line, and here we require many data points. So generally your experimental observations is available in form of this curve, and instead of V and T curve, generally it is drawn between log V and T, and any point you take, and accordingly using this formula, you can, instead of using this formula, you can use this formula, and you can you can have a find out the value of the resistance. So this is generally done. Now somebody was telling that there is an issue of means your discharge will take a lot of time. So to avoid this kind of situation, we have we connect another parallel known resistance across the unknown resistance. So obviously this parallel combination will reduce the resistance, and it discharge will take place at the higher rate, faster rate. So this, in this case, this formula will be R dash, and from this formula you will be able to measure the R dash, and then this R dash is equal to R into R1 upon R1 plus R1 R plus, because they are parallel combination. So from this formula, one of the your R is known, R1 is unknown, so you can calculate the value of R1 from this equation. So this is how means we can speed up the discharge, we can increase the discharge rate by having additional known resistance which is connected across the unknown or testing sample. So this is how this issue can be tackled. Sometime it is done. Now I am taking this example here, which is having this kind of which is based upon this kind of arrangement. So here you see a cable is tested by loss of charge method using a ballistic galvanometer with following result. Just discharge immediately after charging, deflection of 200 division. So here instead of micrometer or ammeter, we are using galvanometer. So obviously galvanometer output you'll get in terms of the divisions. So it is 200 division. Means this is proportional to the initial value up to which your capacitance is charged, then discharged after 30 seconds after charging. So after 30 seconds your deflection is only 126 division, and deflection is 100 division when in parallel with the resistance of 10 mega ohm. So that arrangement, I'm talking about this arrangement here. 10 mega ohm resistance is connected across the insulation resistance, across the insulation, and then after 30 seconds you are getting deflection of 100 divisions only, because more discharge will take place. Calculate the insulation resistance of the cable. So this is in this case, if you look closely, so this is your, in terms of the formula, this formula, if we talk, so or the original formula we talk, this is your original formula. So this voltage is, this deflection is directly proportional to capital E, and in this case T is 30 seconds, and after 30 seconds small v is 126 division when you are using only the insulation, and 100 division when you are using only you are using the insulation as well as a additional parallel resistance of 10 mega ohm. So in any case we are required to calculate the value of the insulation resistance. So here you can see R is equal to, we are taking first case, and then we are getting, because here you see capacitance value is not given, and then this is R dash. The situation when you are connecting a 10 mega ohm resistance across the insulation. So here you are getting 200 divisions, and this 100 division is the after 30-second deflection is only 100 division. Here deflection is 126 division. So we got this R in terms of C and R dash in terms of C. Then we'll take the ratio. So obviously your C will get cancelled, your capacitance remains same, you're not changing capacitance value. So you're getting ratios 0.67, R dash is equal to, and you know R dash is equal to R into 10 mega ohm, R plus 10 mega ohm. So finally you are able to find out the unknown resistance. This is 5 mega ohm. So if you are having any question, you can ask, please. Anyway, this is the last thing. Sorry, mega ohm bridge is there, but I'll close my discussion here today. So if you are having, I'll put all these slides because we are near completion of this unit, your first unit. So I'll put all the slides on the classroom. I request to all of you, you go through these slides and try to understand, comprehend the topic. And if you feel any difficulty in understanding any of the topics that we discussed throughout this unit, then next means tomorrow, I think. Tomorrow is the last chance for discussing the topic related to this unit, because after this we'll switch over to the second unit. So if any difficulty, any topic you are feeling any difficulty in understanding any of the topic in this unit, then I request to all of you, you go through the slides. I'll put after this lecture, I'll put all the slides over there. And if you feel any difficulty in any of the topic, then you're having opportunity on the next turn to discuss it. Okay, to all of you. And as far as this numerical problem is concerned, if you are having any difficulty in understanding any of the steps, you can ask, please. I'm calling the attendance for other students, remaining students. By that time, you can go through it, and if you feel anything, any difficulty in understanding anything, so you can ask after it. Now respond your roll call, please. Roll number 31.
Present, sir.
32.
Yes, sir, present.
33.
Present, sir, 33.
35.
Present, sir, 35.
36.
Present, sir, 36.
37.
Present, sir, 37.
38. 39 or 40.
Sir, present, sir, 38.
38 present. 40.